In this lecture, we will use grouped and ungrouped data to calculate the standard deviation and interpret it within the context of a question. We will also calculate the variance of a distribution. I've gathered all of the different formulas for calculating standard deviation on this screen. Let's just review the symbols and what they mean. Capital italicized S stands for the sample standard deviation. Sigma stands for sum. X by itself means a score in your data set. X bar is the mean of a sample. And N is the sample size. In the second equation, the only things that are different is the S becomes a sigma, which now stands for population standard deviation, and the X bar is transformed into mu, mu being the population mean. The third equation can apply for either the sample standard deviation or the population standard deviation. And what it is it's the raw score formula. The advantage to the raw score formula is that you don't have to calculate deviation scores, but otherwise it is the equivalent of the two formulae we just looked at. So the only thing that's different here is you've got to be careful about which one is the sum of the squared values of the data set and which one is the sum of the values of the data set squared. In this first term, you are going to add up all of the squared data values. In the second term, you're going to add up all the data values and then square them. So that's the difference between them. Then, in the bottom set of equations, we have S hat. And S hat, remember, is the predicted population standard deviation. This is when you have a representative sample and you would like to use the standard deviation that you've calculated from that to predict the standard deviation of a population. In these cases, you do not know what the population standard deviation is. It's used for inference tests. The only new symbols that creep up in here is that we're also going to consider doing a grouped frequency standard deviation. And that's where this little f comes in. That little f says simply take the number of times that value occurred in the grouped distribution and multiply it by the actual value. Let's practice with a small set of data by calculating the population standard deviation. First step is we need to calculate the mean of this sample. If you add up all of the observations and then divide by how many observations there were, in this case 5, you end up with 25 over 5, which equals a mean of 5. In the next step, we will calculate the standard deviation in steps. First, we'll take all of the scores and find their deviations. Then we'll square those deviations. And when we're done with that, we'll sum those squareds, divide by n, and take the square root. So here goes. My observations are 5, 7, 2, 4, and 7. To find the deviations, we're going to subtract the mean from each of those. So 5 minus 5, so that's my observation minus my mean, equals 0. 7 minus 5 equals 2, deviation score of 2. 2 minus 5 takes me into the negative side at negative 3. 4 minus 5 equals negative 1. And finally, 7 minus 5 equals 2. To square these values, you multiply it by itself. 0 times 0 is 0. 2 squared, or 2 times 2, is 4. Negative 3 quantity squared, to make sure that negative goes away, is negative 3 times negative 3, or positive 9. Negative 1 squared equals positive 1. And 2 squared again is 4. So now we have the squared deviations. We need to find the sum of the squared deviations. Recognize the symbol sigma, meaning add them up. And then in parentheses, x minus x bar, parentheses squared, all that says is add up the last set of numbers we just calculated. 4 plus 9 plus 1 plus 4 equals 18. So we're about halfway, a little bit more than halfway done with the formula, because I know that the formula to calculate the population standard deviation has the sum of the squared deviations on top of the fraction. And on the bottom, n. For this data set, we had an n of 5, so I'm going to substitute in our answers, and you get a square root of 18 over 5, which is the square root of 3.6. There it is. Square root that puppy, and you get a final answer. The population standard deviation for this data set is 1.897. I'm going to go ahead and use good rounding rules. If I want to keep 1.89, the 7 bumps the 9, which then bumps the 8, so the answer is 1.90 is the standard deviation for this small set of data. Okay, let's do another example. This data set has 4 values, and I want to calculate S hat, meaning I want to take these 4 values and then use them to generalize about a population that it represents. Just like last time, I'm going to start by calculating the mean. So I add up the 4 observations and divide them by 4, and you get a total of 24 divided by 4, which equals 6. So the mean for this data set is 6. Setting up the same type of grid I did in the previous example, I'm going to start by listing all of the scores. Then we'll calculate the deviations. Then we'll square the deviations. And then we'll finish the problem by adding them up, dividing by n, and taking the square root. So here they are, 7, 7, 6, and 4. With a mean of 6, my deviations are 7 minus 6 equals 1. And again, 7 minus 6 equals deviation score of 1. 6 minus 6 gives me 0. And 4 minus 6 equals negative 2. I know I've done this right so far because my deviations all add up to 0. Now we'll square them. 1 squared is 1, of course. And again, 0 squared is simply 0. It's a nice, easy set of data. And negative 2 times negative 2 becomes positive 4. Now, add all these guys up, and that gives you the sum of the squared deviations. In this case, that equals 6. Now, let's finish off the formula. If I'm looking for S hat, the hat's going to come back on that S there in just a second. I need the sum of the squared deviations all over n. In this case, n is 4. And since it's an S hat, I need n minus 1. And your book does a nice job of explaining why. So I advise you to take a look at Spatz's description for that n minus 1 in the denominator. Put all of this data in, you get the square root of 6 divided by 3, which of course is the square root of 2. Plug that in a calculator and you get an answer for your S hat of 1.41. In both of the previous examples, we used what's called the deviation score formula for calculating the standard deviation. This time I'd like to use the raw score formula. It involves setting up a table that's different than the ones in our previous samples. In this table, there are only 2 columns. One column for the actual observation scores, in this case 2, 3, 7, 8, and 5, and the other column for those scores squared. After you set up the columns, you're going to calculate sums for them by adding up all the things in the column. So if I add up all the observations, 2 plus 3 plus 7 plus 8 plus 5, I get a sum score of 25. And then for the squared terms, let's square them first. 2 times 2 is 4, 3 times 3 is 9, 7 times 7 is 49, 8 times 8 is 64, and of course 5 times 5 is 25. Excellent. Now, add those terms up, you get a larger number because they're bigger, obviously. I believe it's a 151. Yep. 151. Now, the red values up there, the sum of the observations, in our equation we actually need the sum of the observations quantity squared. So I'm going to show you how to notate that. If you put the sigma x in parentheses and the square outside, it says to take the sum of that 25. That was the sum of the observations and square it. 25 times 25 is 625. Having that square on the outside makes a big difference, so you got to be careful. Alright, now plugging into the formula, I know that I'm going to have to work with an n of 5, and on top I'm going to have the sum of the squared terms minus the sum of the terms squared over n. Notice how I said that just slightly differently, because that's how they are differently interpreted. So, plug and chug. The sum of the squared terms is 151. Subtract 625 divided by n is 5. All over 5. Keep plugging through. You know that you need the square root of 151 minus 625 divided by 5 is the same thing as 151 minus 125 over 5. Keep working it into more condensed forms, and you end up with s is equal to the square root of 5.2. Now go to your calculator, take the square root of 5.2, and you get an s of 2.28. Final answer, the standard deviation of this sample is 2.28. The prompt in this next example tells us we need to take these scores and treat them as a sample that we want to use to generalize to a larger population. I'm going to use the raw score formula for an S hat. So just like in the last example, we're going to set up columns for x and x squared, put in our observations 2, 2, 4, 6, and 7, and the x squared column, 2 squared is 4, 2 squared is 4, 4 squared is 16, 6 squared is 36, and 7 squared is 49. Now we need to add them up. 2 plus 2 plus 4 plus 6 plus 7 equals 21. And 4 plus 4 plus 16, see that gets me to 24, plus 36 is 60, plus 49 is 109. Now, for my equation, remember I'm going to have to keep track of which one is the sum of squared values and which one is the sum of the values squared. The first thing in my term is the sum of the values squared. No, the sum of the squared values. Yeah, that's right. Sum of the squared values. All right, so just play the matching game. You can see how easily it can be to get confused. So you have 109 minus, all right, I need 21 squared because those are the sum of the values, and then I need to square that sum of the values. so 21 squared, over an n of, I believe, 5. 1, 2, 3, 4, 5. N of 5. So it goes 5 on the bottom of that fraction, and then 5 minus 1 on the bottom of the whole shebang. All right, let's work on putting this into simpler terms. If I take 21 times 21, you get a pretty big number, which is not a surprise. You get 441. So now when I put it into the radical this time, I'm going to take 109 minus, and then 441 divided by 5 equals 88.2. Divide that difference by n minus 1, which is 5 minus 1, or 4, and you end up plugging it into your calculator as being s hat equals the square root of 5.2. So type 5.2 and hit the square root button in your calculator, and you get s hat for this set of data equal to 2.28. The next example has a scenario around it. Suppose these scores were ratings of 5 people in a restaurant about how much they liked a particular brand of salsa. We want to use the sample to infer population of all the people in the restaurant. So we want to use the S hat formula. And I've chosen to use the S hat formula for the raw score simply because calculating deviations can sometimes get messy. So setting it up like we have previously, I have a column for the scores and a column for the squared scores. 5, 7, 9, 6, 7 are our 5 pieces of data. 5 squared is 25, 7 squared is 49, 9 squared is 81, 6 squared is 36, and 7 squared is 49. Now we're going to add these guys up. The sum of the observations is 34, and the sum of the squared observations is 240. Now to get them into the formula under the radical in the right places. S hat is equal to, big square root sign, give myself plenty of room. All right, I'm ready. So the first sigma term is the sum of the squared terms, so that's 240. And minus the second term on the top has the sum of the observations squared. So the sum of the observations was 34. Now I need to square them. 34 squared goes on top. And n, of course, is how many observations we have, and it's 1, 2, 3, 4, and 5 again. 5 observations, so it's going to go in 2 places. There, and then on the very bottom as n minus 1. Oops, I was circling them in the wrong one. Sorry. Very similar, though. 5 minus 1. There we go. All right. S hat. Let's finish cleaning this up. 34 squared is the same thing as 34 times 34, or 1156. So my S hat should now look like 240 minus, see, 1156 divided by 5 gives me a nice number, 231.2, all over 4. Keep working. 240 minus 231.2, divide that number by 4 gives you 2.2. So this S hat is equal to the square root of 2.2. So final answer, S hat must equal 1.48. The sixth example. In this, we have a very small population because it indicates that these scores are all that exist for an entire group. So we're going to calculate a sigma. So that equation, let's go back just for more practice using the deviation score formula. First thing I need to do is calculate the population mean. So I'm going to add up my observations, 3 plus 4 plus 1 plus 1 plus 4, 7, 8, 9, 10, 11, 12, 13. Divided by 5 is, okay, so mu is 13 divided by 5, which is 2 3/5 or 2.6. Good. I'm going to get fractions. Blah. If you really hate the idea of working with decimals, which are just fractions, then use the other formula. But we're going to do it this way just so you can see that either way will work just fine, as long as you're organized and careful. So here are my columns for the scores, the deviations, and the squared deviations. My scores were 3, 4, 1, 1, 4. Now subtracting the mean of 2.6 from each. 3 minus 2.6 equals 0.4. 4 minus 2.6 is 1.4. 1 minus 2.6 goes negative 1.6, and that's there twice. And then there's another 4 minus 2.6. 0.4 times 0.4 is 0.16. 1.4 times 1.4 is 1.96. 1.6 times 1.6 is 2.56. And then another 1.4 squared, 1.96 at the bottom. Okay, now I need to add up my squared deviations. Punch those through your calculator most likely, and you end up with a sum of the squared deviations from the population mean of 5, 6, 7, 9.2. Okay, so finally sticking it into the overall equation, I now have a numerator of 9.2 and a denominator of n. And again, we have a very small data set, in this case 5 pieces, so n on the bottom is 5. So sigma equals the square root of 9.2 over 5, which is the same thing as the square root of 1.84, giving me, finally, when I hit that square root button, an answer of 1.356, which rounds to 1.36. Okay, for the final example, we're going to start with a little bit of the work already done for us. In this example, they've stated we're working with a sample of 10, and further, we want to use that sample to generalize a larger group. So we want to choose the S-hat formula. And specifically, I want to choose the raw score formula this time because of the data that are already provided. They've already provided us the sum of scores, which is sigma x, that's 12. And they've provided us the sum of squared scores, which is 100. Combine that with the fact that n equals 10, we have everything we need for the equation already. So if our equation is S hat is equal to the square root, really big square root, give myself lots and lots of room, and then, yep, set up. Now I just want to make sure I choose the right things. First off, I need the sum of the squared values. That's the first term, and that's 100 in this case. Then I need to subtract, and then on the top of this fraction, we need the sum of the scores squared. The sum of the scores is 12. 12 squared is 144. The problem has an n of 10, so 10 will go in 2 places. First underneath 144, and then on the very bottom is 10 minus 1. And I forgot the little equal sign. There we go. So S hat equals, break this down a little bit more. 100 minus 14.4, because I just moved the decimal place when you divide by 10, all over 9. Now if you take 100 minus 14.4 in your radical, now you will have 85.6 divided by 9. Plug that into your calculator, and it tells you that S hat is equal to the square root of 9.51, and then it's 11111. So I just kept a couple of them. Hit square root, and finally the answer for this sample, the standard deviation that you can generalize to a population, is 3.08. One of the really convenient things about calculating the standard deviation the way that we have is that we've actually learned something that we'll need in the future when we start our tests of inference sections. We've learned how to calculate the variance, because the variance by definition is simply the standard deviation squared. So really, it just means that if you skip the very, very, very last step in your standard deviation calculation, where you hit the square root button, that number is the variance. So if I gave you an example where I told you the standard deviation was 2, and I asked you for the variance, the answer would be 2 squared, or 4. If it were 16 for standard deviation, then you would take 16 squared, 256, for the variance. Altogether, really very, very straightforward. We'll use the variance later on when we do an analysis of variance inferential test of means. But for now, just be able to understand the relationship between the two things. Finally, Spatz introduces error bars as a way to graphically demonstrate both a mean and a standard deviation. These bars have heights corresponding to the category's means, and the vertical line represents plus or minus 1 standard deviation from that mean. This representation is handy because it allows you to look at the bigger picture of how data are different.